Hi everyone. Yes, I'm Stanley. Where's the... Okay. I'm going to mow through this because I've got like half an hour worth of slides and 10 minutes to do it. Okay. Extended periods of low wind may have contributed to the elevated reef water temperatures seen during the 2017 bleaching events. And these episodes were correlated with periods of observed bleaching. That's what part of what I'll be presenting. As a consequence of the low wind, evaporation and surface mixing are reduced, and these effects can be seen during the event, in the data obtained during the event. And the question I seek to explore towards the end is, under these conditions, could an intervention which augmented natural mixing and flow have reduced the severity and bleaching mortality during this event? All the data that I use in this talk is publicly available. I've used AIMS data and IMOS data and some Eye on the Reef data. So many thanks to all the data providers. Okay. There's a relationship between wind and the ocean surface conditions that I think other people have dealt with, and I probably don't have to go into. Suffice to say that the wind is inputting kinetic energy in the form of motion, and that's driving mixing processes. But the other thing it's critically doing is it's promoting evaporation off the ocean surface, and that's a cooling influence. And the combined effect of this, and when those are missing, we have a net input of heat into the water column because we're not taking as much out every night during without the wind being there. And we also have it being concentrated in the top of the water column because there's not as much mixing going on. Okay. We took data from the AIMS weather station at Agicor, from the Reef AIMS in-reef data loggers, the air temperature loggers, and we had that glide emission during the 2017 bleaching event. It went in sort of at the beginning of March, and we got sort of probably about 6 or 7 days of being in that sort of period of the area of the Great Barrier Reef before moving off into Palm Passage, where it's sort of not really relevant to the sort of area that we're talking about. So that's the Reef area with the data loggers there and there. The reef slope one at 9 metres and the reef flat one at 2 metres. Okay. That's the glider path track, so it makes its way through the reefs on its own, creating vertical profiles as it goes. Okay. Low wind was a characteristic of the 2017 bleaching event. A lot of work has been done linking low wind periods to the severity and of coral bleaching and the mortality and the chances of them recovering. I will go into that if anyone asks me later. What a indicator, a threshold level of 3 metres a second, is defined by NOAA as a doldrum day. And it essentially represents the period through which normal, or the threshold below which normal atmospheric sea and atmospheric ocean interactions have sort of been disrupted. Okay? If you apply that 3 metres a second threshold to the Lizard Island and Agicor Reef weather station data, you see that 2016 and 2017 was a real standout year for doldrum days, with like 4 times as many out of the Lizard Island data and twice as much out of the Agicor Reef data. So could these strings of doldrum days have contributed to the severity of bleaching and mortality? I think through a lot of the other talks we've already seen the answer to that, yes. Okay, if we look at the AIMS data loggers, these have been in for 20 years, not continuously for 20 years, but over a time period of 20 years. And what that enabled us to do is create a climatology, of what an average year looks like over those 20 years, and that enabled me to produce this in-water climatology. The red line is daily temperatures from the beginning of summer, daily average temperatures, for the 2017 event. Okay? And what we want to point out is this very hot January, this disastrously hot March, okay, and not quite as hot February, but still pretty terrible. Okay. The other thing I'd like to point out is this seasonal maximum of 29.3 degrees. That's generally accepted as what the coral in that area is adapted to living in. So when we talk about elevated temperature for a particular species of coral or a particular area, it's normally related to what the corals in that area are acclimatised to, and in this case, the more regular logger comes out to 9.3 degrees. Okay. The bottom graph essentially represents the same thing, except instead of absolute temperature on this side, we've got degrees from normal. It's a temperature anomaly graph. Okay? So any time that red line is below 0, when we're cooler than normal, and every time it's above it, then we're warmer than normal. Okay? The blue line is tidal flushing. That's essentially total aggregate tide height for the day. So we have the peaks are spring tides, and then the minimums are the neap tides. In the green triangles, they represent the days that were doldrum days. Okay? So we had a little period of calm weather in the middle of January, and this really horrible string in March. What I want to point out is that during these strings of doldrum days, your temperature normally ratchets up day after day. Okay? And we'll look at the collider data and explain that process. But that's how this string of doldrum days, 1 or 2 doldrum days isn't a problem, but if you get 4 or 5 in a row, each one incrementally ratchets up the temperature. What's happening is energy is going in through the sunlight, but it's not being evaporated completely every evening. Okay, so let's look at the glider data. This is glider data. Okay? There are 250,000 individual temperature measurements making up this image. Each dot is a temperature measurement whose colour codes the temperature that it measured at that point. This was during the bleaching event and around about this sort of central GDR region. The first 3 days were relatively normal wind events with an average wind speed of about 6 to 7 metres a second. And the last 3 were doldrum days. Okay? What we want to point out is early here, when you had heating events, the daily energy from the sun got mixed through the whole water column, and during these doldrum days, it was concentrated at the top of the water column. Okay? So now we've represented the glider data as a depth profile. Okay? We have depth in this direction here, and horizontally we have temperature. And I've split them up into measurements taken in the afternoon and measurements taken in the early morning. Okay? So essentially the red area is daytime heating and the blue area is nighttime cooling. Okay? This is after 3 relatively normal windy days, and this would be the normal situation you'd have on the GBR itself. Okay? So what we see, the big blue dots are the reef logger data, the 2 and the 9 metre AIMS temperature logger data for the same time and period and position in the water column. Okay? What we see is when the loggers are sort of trapped in shallow water, they don't have any, on the reef flat, they don't have any deep water at their disposal. So all the daytime energy is going into a small surface body of water, but it's balanced by the nighttime cooling. So you have this exceptional transition in the reef flat, but that's perfectly normal. That's associated with the spring tide putting the logger into shallow water and then having daytime heating operating in a very small water column and nighttime cooling. And the 9 metre data there is conveniently pretty well located with the glider data. Okay, what happens after some doldrum days? This is 3 doldrum days in a row. What we see now is intense heating in the top of the water column, all the way up to 31.5 degrees. We see the coral in the reef flat logger also subjected to that. And we see that this temperature here, this daytime temperature, is being dumped into the top of the water column, the top 15 metres of the water column, and we're not getting anywhere near as much nighttime cooling. So you can see the nighttime logger there is sitting at the temperature of the surrounding water. It's no longer being cooled by evaporation on the reef flat. Okay, so that happens day after day after day, and this temperature here gets dumped into the top of the water column, and that gets dumped into the top of the water column, and we see this incrementally stepping up of the temperature anomaly day after day. The glider came back into that period, into the same spot, 3 weeks later. Okay? And that's what the glider saw when it came back. Completely mixed all the way through the water column, the daytime energy being immediately distributed down through the water column, and about a degree cooler than before. So Cyclone Debbie passed a few hundred kilometres to the south, but obviously the wind and the energy created from that completely mixed the water column and provided some cooling and a drop in solid radiation from the clouds. Okay, so what I did with this slide was averaged all of those temperature measurements, all those order of a million temperature measurements, into average depth profiles. The blue ones are for the first 3 windy days, and the red ones are for the last 3 doldrum days. And what you can see is below 10-15 metres, the profiles are identical. But in the surface of the water column, there is a definite departure from normal associated with the calm winds. So the calm winds have put more energy into the water column by shutting down an evaporation or by reducing an evaporation. And they've also stopped that energy being distributed through the water column because they've shut down the surface mix. Okay. This slope here is 1 degree Celsius per 60 metres. Okay. And you know, it's an interesting number. 4 minutes. Okay, how that relates to the bleaching. Eric Fisher provided some information for me from Reef Magic. Observed bleaching was first. Observed bleaching happened here on the 18th of January. That was associated with a neck tide, calm weather, and this high anomaly. So when you have that high temperature, calm, not all at the same time, you get a problem. Okay. Same happened in the February 17. A few days delayed because there was some southeast winds here that kept things cool. And then we had this terrible March associated with long strings of doldrum days. And the eye on the reef data showed that 2,000 colonies were affected during that period. Okay. So if the problem is mixing, how much energy is involved in that stratification, right? And that's a key question to ask if we're going to make an intervention. So the way engineers solve this problem is to set up a hypothetical situation and solve it, right? So here we have a hypothetical situation with a 10-metre water column with a 1 degree temperature difference. Okay? So the top 5 metres at one temperature and the bottom 5 metres at another temperature. Most engineers will set this up as a pumping problem, and that makes it hard to solve because the head changes throughout the process. Also, a very common mistake we're treating this as a pumping problem is not account for the inlet pressure when calculating the head. The initial static pressure in this problem is not 10 metres that you might first think. It's 2 millimetres, okay? And it's associated with the difference in density of the two materials. All right? The easiest way to solve this problem is the way oceanographers solve it. I happen to know an oceanographer, so I asked him. Okay? And what they do is they evaluate the potential energy of the water bodies in the test state, which is unmixed, and compare it to a reference state, which is mixed. And if you do that, the solution comes out very easily, and it's about 42 joules per square metre. Right? 1 kilometre by 1 kilometre by 10 metres by 1 degree Celsius. Okay? That's twice as big as Mr. Mars's get on with it 50 hectare challenge. This is 100 hectare. Right? If we were to, how much energy is involved in that stratification? It's about 12 kilowatt hours. The system with 20% efficiency could resolve that situation with 60 kilowatt hours worth of energy. What does 60 kilowatt hours look like? It looks like 2 minutes operation of a passenger ferry. It looks like 22 minutes operation of a tourism joy fly helicopter. It looks like 2 hours operation for an outboard, or 7.5 hours of a portable genset. So, to answer someone's question from before, no, we do not need a coal-fired power station to solve this problem. It's surprisingly little amount of energy involved in that stratification. Could a system like this have mixed the water before it got onto the reef at Moore Reef and created a temperature relief in the order of 0.5 degree Celsius during those doldrum days? So the key aspects are, it's not a lot of energy. It doesn't have to go in the whole season. It just has to go in for the times when the doldrum days are, and it's achievable at the scale of a tourism site. Okay. Thank you. 13 seconds to spare.